Everyone. Today, I, Aman Gupta, and my group mates Yashashvi, Advait, and Vipul are going to present you on the topic cyberbullying detection with Spark. So, first we will be giving an introduction of the topic, then we'll be covering the PySpark area, then we'll be covering the problem space statement, and then we'll be talking about our work. Introduction. So, what is cyberbullying? Cyberbullying is nothing but a harassment or in the form of electronic means. It has been become increasingly common, especially among teenagers, as the digital sphere has expanded and technology has advanced. Our project aims to not only raise awareness about this social issue but also propose various machine learning techniques using Apache Spark's ML library that can be used to tackle cyberbullying in real time by utilizing the distributed processing fashion and access to remote systems that Apache provides. So, this is a gist of things that we did. We collected the secondary data, then we pre processed it, we did model training, and then we did model evaluation. But before that, what we did is we set up a multi-node cluster on Hadoop. So the this is the overview of the Hadoop master node screen on the website. And as you can see, we have set up around three slave nodes and we have connected it to the master node. And you can see the health of all three nodes and what capacity it is filled to. Now, this is my base program, Python program, and here I have given the user a complete menu-driven system where he just have to just log into it and just do whatever he wants to do. Either he wants to list out his contents, whatever he has already uploaded to his cloud distributed multi-node cluster, and either he can just upload it, either or he can download those files, and also he can delete those files. Made it relatively very easy for the user of this program to just upload the files and the algorithms to the in a distributed computing fashion. And I've also made it where I've also given a choice for the user to select the chunk size for the file to be uploaded, right? So the user can select the chunk size as 16 MB, 32 MB, and 256 MB according to his choice, and that particular file will be sent it over to the my slave nodes with in 16 MB chunk or the 32 MB chunk or the 256 MB chunk. It all depends on what user wants. So you can see this. For now, we started with making the multi-node cluster. Vibhul will cover the topic of PySpark.
PySpark is the Python API for Apache Spark, an open source distributed computing framework and set of libraries for real-time large-scale data processing. Although it's not very fluid to work with, it has a lot of inconsistencies with Java, on which it is built, and also with Python libraries. So the module which I used for encoding my data is TensorFlow Hub's Universal Sentence Encoder. So this module is approximately of about 1 GB. Depending on your network speed, it might take a while to load the first time you run inference with it. After that, loading the model should be faster as modules are cached by default. Further, once a module is loaded to memory, inference time is relatively fast. The module does not require pre-processing the data before applying the module. It performs best effort text input pre-processing inside the graph. So semantic similarity is a measure of the degree to which two pieces of text carry the same meaning. This is broadly useful in obtaining good coverage over the numerous ways that a thought can be expressed using language without needing to manually enumerate them. Simple applications include improving the coverage of systems that trigger behaviors on certain keywords, phrases, and utterances. The universal sentence encoder was partially trained and custom text classification tasks in mind. These kinds of classifiers can be trained to perform a wide variety of classification tasks, often with a very small amount of labeled examples. Let's go through the code quickly. So here we are converting the text format to document format and using the universal sentence encoder to encode the records. Here you can see the results of the pre-trained DL model on a different data set that we have imported. The pre-trained DL model was that we have used works on classifiers, and the result on the decision on the pre-trained model that we've used. So next, this is the decision tree results that we have required using PySpark. The zero output in the results column uh, implies that it's not offensive, and one implies offensive according to the model, and then we kill the Spark context. So here is the precision, recall, and F1 scores of the pre-trained model, and here is the recall accuracy and precision scores of the decision tree classifier. Now, Yashasvi will continue.
In our work, we have used 5 machine learning algorithms. The first one is logistic regression. The second, naive Bayes. Third, decision tree. Fourth, random forest. And the fifth one, support vector machine. Our dataset looked something like this, where we had textual comments from social media sites, and they were tagged as 1 or 0, depending on whether they had a bullying comment or a normal comment. This is a comment which does not contain any cyberbullying text. Now, we all know that algorithms cannot simply deal with the text or strings that we usually use in social media sites. And this has to be converted into something that can be captured and learned by algorithms easily, which is numeric data. To do that, we need to pre-process our data, which can be done easily by count vectorizer. Now, count vectorizer gives us a lot of algorithms for working with the feature and even extracting features from our raw data, which was our aim for this particular usage. We can also transform our features and select a subset of features from the large number of features that might be available. Let's see how count vectorizer works. So if we have two sentences, hello, my name is James, and this is my Python notebook, we can identify which vocabulary exists in the sentence 0 and which exists in sentence 1. As you can see, the vocabulary word hello exists only in sentence 0, but the vocabulary word is exists in both sentence 1 and sentence 2. Now, the other concept that we have used is term frequency and inverse document frequency. Term frequency and IDF is a feature extractor that the Spark ML provides. Term frequency is defined as the number of terms that appear in a document. Terms in documents are independent variables, and term frequency is dependent on these variables. Now, in order to understand what inverse document frequency is, we first need to understand what document frequency is. Document frequency is defined as the number of documents that contain a particular term. And here, document frequency and the document corpus are independent, whereas document frequency is dependent on both of these different independent terms. Independent IDF or inverse document frequency can be described by a simple formula. For example, IDF for a term T in a document corpus capital D is nothing but log of the number of terms, the number of documents that exist plus 1 divided by the document frequency of that particular term. If we multiply TF and IDF, we can get why a particular term or how important a particular term is in a document corpus. Let us understand this with a simple example. Okay, so here we have 3 documents. Let's say we want to calculate the term frequency for the word cloud in document 1. Here, cloud is only once, so the term frequency will be 1. If you want to find the document frequency for the word cloud in the whole corpus D, where this collection document is our document corpus, but as you can see, cloud is in document 1. It also appears in document 2 and also appears in document 3. So it appears in all of the 3 documents. So the EF for cloud will be. Then we can calculate IDF simply by taking the log of all the documents, which are three, adding one to that, dividing that by the DF, which is 3 again, adding one to that. So here DB equal to above 1. And this is how simply we find TF, DF, and then subsequently IDF. Now we can multiply TF and IDF to understand what is the importance of a particular term in the document corpus. This is an important feature and can really help people to understand easily what we are talking about, thus get better patterns and learn much better than what it would have learned without providing TF-DF features. Thank you so much. Now Advait will be showing how our code works.
Okay, so let us now see the working code of our trained models. So this is the Maven project that we have created for this project. Here the pom.xml file contains all the dependencies required to use Spark with our Java project. So coming to the knife-based.java. So the simple model.java file contains the bag of words implementation, and model tfidf.java contains the tfidf in place of bag of words. So here, first of all, we have imported all the libraries that will be used to train the model. So after that, we have created a Spark session. Here we have written is a local star. So local star tells the Spark to use all the available codes on our machine. So after that, we have imported the data set that we are using to train the model. Here we are using a pre-built tokenizer to separate words from the comments in our data set. After that, we have used a random split function to split the data set into 80:20 ratio. We have used 80% for the training purpose, and we have reserved 20% for the testing purpose. After that, here we have count vectorizer function that is basically the implementation of bag of words model. And then here we are calling the knife based function to fit the data set, fit the model with our data set. After that, we are calculating the accuracy on the training set that we had reserved for the testing purpose. And similarly, we have trained the second model like knife-based tfidf.java. We have simply changed the count vectorizer with this tfidf function. Okay, so now a short introduction about the algorithms that we have used in this project. So logistic regression simply uses this function to fit the model, and knife base is based upon the Bayes theorem for conditional probability. Support vector machine tries to maximize the gap while differentiating two classes. Decision tree creates multiple child nodes based on conditions to do the classification. And SVM classifier is a boosting algorithm that trains multiple decision trees by taking bootstrap samples from the dataset. Now, this is the result that we have got from our trained models. We found that SVM classifier is giving the best accuracy with our dataset. So for now, we have used only a single machine to train these models, and even our dataset was small in size. So we will extend our work to use multiple node cluster setup, and we will try to use some actual big data to train these algorithms. So this is our team, and thank you everyone.